Hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today as it is every day here in my virtual classroom. Step on aside as we jump into the Chapter 5 review in the Big Ideas Math Integrated Math 3 textbook. This is all things with exponential and logarithmic functions. We're going to be transforming them, evaluating them, graphing them, describing them. I don't know. We're going to be doing a lot of things with them. So expanding and condensing, that's in the logarithmic portion. Everything in logarithms is brand new for you here, and hopefully through this, I think, 36 question ordeal, we can get everything taken care of. If you want to download this PDF, jump to the description section down below. You'll find it there. You can find the timestamps for each individual problem, as well as PDF for a graph paper in case we need to do any graphs. Without further ado, I'm going to go ahead and get started. Section 5.1 was all about the natural base e. Now, e is around the number 2.7-ish. There's like 2.71828 something, something, something. It's irrational. It's a constant. It represents natural growth. It's called the natural constant, Euler's constant. And we can use things with it. I don't know if you understand everything that's done with it yet outside of continuously compounding functions. There are more things you'll learn in calculus with it. But for now, we need to understand some of the numbers and what they are, or at least put them to good use, find out where it is on the calculator. So in the example question, it says, tell whether y equals e to the 0.5x represents exponential growth or exponential decay, then graph the function. Now here's the answer portion. So we can see the graph looks like growth, but what made this one growth as a thing? Remember, e is a number. It's not a variable. It's around 2.7. The fact that the number itself is greater than 1 means it needs to have the x's increase, not the x's, the exponents increase over time for the number to increase. So as long as this 0.5 is a positive number, you're going to see an increase in the exponent. That means you're going to see growth. 2.7 raised to higher powers is higher numbers. So this represents exponential growth because r is 0.5. They mention a being a positive 1, which I want to just talk about the fact that there's an invisible 1 right there. That a being 1 is positive makes it represent exponential growth. I disagree with that. It makes it positive growth, but there's also such thing called negative growth, which would look like that. So it's possible to actually have negative growth in cases like that, and honestly, we weren't doing too many negative graphs to begin with. What makes it decay is if r was a negative number. Now, this isn't your general graphing form that we do. Outside of e, it is. But if this is a negative number, now you're dividing by amounts of e as your exponent increases, or as x increases. So that would be decay, and decay would look like this instead. It would be approaching the asymptote. So how do they get their graph? They go and use a table. I'm probably not going to use a table per se. I will use their table. And they substituted specific x values. These x values are because the r is 0.5. 0.5 is 1/2. That means there's a horizontal stretch by a factor of 2. That means you have to plug in double the x values to achieve the same y value that you would if the 0.5 wasn't there. Case in point, e to the first power is the 2.7 number. E to the second power is 7.4-ish. E to the 1/3 power is around 0.3. E to the 1/3 power. E to the negative first power is around 1/3. It's around 0.37, and then e to the 0 power, of course, is 1. Anything to the 0 power is 1, which is going to be important for future graphs. But here's your graph. It's the same as the e to the x function, except it's stretched by a factor of 2 horizontally. So there's the graph, there's the growth. That is the example. We move forward. Let's look at numbers 1, 2, and 3, which have nothing to do with graphs, but just use of e. Now, these ones are no real different than what we were actually doing in the previous chapter, although we were focused more on rational exponents and radicals. We are simplifying these expressions, e to the 4th times e to the 11th. No calculator use is expected in these problems. All you're doing is adding. You're just adding the 4 and the 11, and you get 15. Again, keep the base, add the exponents when you multiply two bases featuring exponents. And that's it, e to the 15th. It's a number in the thousands, tens of thousands, whatever it is, hundreds of thousands, but we're not actually evaluating the irrational value. Just making sure we know how e can work just like any other number. Number 2, we have 20 e cubed over 10 e to the 6th. My personal way of working these out, I divide 20 by 10 to get 2. Who wouldn't do that? E cubed over e to the 6th, you do 3 minus 6, and you get negative 3 as your exponent, which means it's positive in the denominator. What I do is I remove all 3 e's from here, 3 e's from down here. You're left with 3 e's on the bottom. This is 2 over e cubed. 2 on top, e cubed on bottom. That's your result. Itchy eye syndrome ahead. Are we here? Number 3. Negative 3e to the negative 5x squared. Ooh. Okay. Okay. Your choice on how you want to go about negative exponents. I generally turn them positive by the end, or in a fraction problem. I do it in the beginning. This isn't a fraction problem. Not yet, anyway. We're going to square this. That means we are going to square negative 3. And we are going to be squaring e to the negative 5x. These both have two different things going on with them. Squaring negative 3 is negative 3 times negative 3, which is positive 9. Squaring these two, which is multiplying two of these, which is adding two negative 5x's, or doubling them. So this is e to the negative 5x times 2. Those are multiplying. So that's 9e to the negative 10x. We don't like positive. We do like positive exponents. We don't like negative exponents in our answer. So we're going to turn this one positive as 9 over e to the positive 10x. The 9 does not go down with the e. 9 is not being raised to a negative exponent. 9 is raised to the first power. And that's the result. Make a prettier looking 9 than I did. Let's take a look. And that's numbers 1, 2, and 3. No graphs. Although we're going to start graphing these next ones, and these ones are going to resemble the example problem that you see above, at least with respect to instruction. So numbers 4, 5, and 6 tell whether the function represents exponential growth or exponential decay, then graph the function. As the example stated, at least the one part that I care about, given that all these a's are positive, we could talk about the part that I care about, which is r. R is a positive number here. The r is the number multiplying by x, essentially. It's a 1. Because r is 1, 1 is greater than 0. R is greater than 0. This makes this exponential growth. As exponential growth, you'll see the graph also take off up and to the right, just like this one is. And I'm going to use the tall graph paper here. Now, they have some table values, which are interestingly of note, that we can sort of utilize as well, given that, you know, if I plug in certain numbers for x, I'll show you what e to the x is in this case. I'm not really going to go to x, y. I'm going to talk about x and e to the x and just utilize this for future problems. Then we'll get the 1/3 e to the x if you'd like to, which is what this one's all about. There's a compression, a vertical compression factor to this. When x is negative 1 and 0 and 1 and 2 and 3, we're getting some of the following e values. Now, e to like the decimals, and I'm going to round to just one decimal place even. This is well, this one I'll say 0.37. The other ones I'm going to say around, this is 1 and 2.7 and 7.4 and 20.1. Now, we're going to divide those. Oh, we're going to divide it by 3. Let me also get e to the 4th power with you. E to the 4th power is around 54.6. So 54.6. Normally, because I don't know that one, normally I wouldn't use that, but in dividing it by 3, I think I will. So let's divide some of these numbers by 3. 0.37 divided by 3, it's around 0.12. You know, it's just a small number. This is what we're going to be doing when we actually graph this one. Let's get these ones scrolled up a little bit if we can. Hold, please. Okay. 1/3. 1/3, it's around 0.3, right? 0.33, whatever you want to call that. 2.7 divided by 3 is around 0.9, 7.4. See, normally I wouldn't do a table, but the fact that you have to do these decimals dividing it by 3 is probably something I got to take care of. 7.4 divided by 3 is, I don't know, 2. Oh, geez, I'm having trouble with that one. 2.5. Well, it's kind of 2.5-ish. I'm going to err to the side of 2.5, given that that would be 7.5 if you tripled it. 20.1 divided by 3, 6.7. And this is around 18. Remember, these are rounded numbers, but this is 18.2. So these are numbers we can plot when x is negative this, y is, or when x is this, y is that. The idea here also will involve this horizontal asymptote. You can never get 0. You can never get 0. You can get closer and closer to it, but never actually 0. So 0, 1 is generally where I would start with. Oh, we're taking 1/3 of it though, right? So 1/3 of 1 is, you know, the 1/3 or 0.3. We would normally go up 2.7 right here. We got to divide that by 3, get around 0.9. And then 2.5-ish. Remember, it was around 2.4, 2.5, whatever it was. 6.7. 6.7, I believe. 18.2. This goes up to 17, so 18.2 would be at about right there. Now, dividing these by 3, you get 0.12. Again, how am I going to be able to plot that and make it any different than 0.13 or 0.1? So this is my graph. It is vertically compressed. Normally it has a little bit of a taller set to it. This is 3 times shorter than it normally would have been. But it is exponential growth. This is number 4. All right, number 5. Y equals 6e to the negative x power. Now, they're already really pushing the envelope when it comes to what I got to do. It seems like I really do have to emphasize using a table for these. And I say that with a little bit of angst, yet with a little bit of succumbing to defeats there, because I should probably be. This is negative R value. This will make this exponential decay. That means the graph is actually going to go in the other direction, like that. So given that it's exponential decay, what's happening here basically is you're dividing by amounts of e as x increases by 1. Now, what we can do in a table, again, is we can substitute values for x, get values out for y. That's all up to you. But everything's going to be vertically stretched by a factor of 6. So honestly, I'm not going to get many points out from this one. I think we'll still get points out on the positive x end, more so than the negative x end, because they're about to be multiplied by 6. So let's maybe put some of these ones in. You see, when I do y to the 0 power, that's 1, but times 6 is 6. So this is already vertically stretched by a factor of 6 up here. When I divide 6 by e, because that's 6e to the negative first power, I'm actually going to do that in my calculator right now. 6 divided by e. 6 divided by 2.7 is around 2.2. So let's use it, 2.2. And that number divided by another e, divided by e squared, gets me 0.81. So I'm within the ballpark of actual numbers that I can use on this graph. When multiplied by 6, they're big enough. Now, -1, when I plug in a -1, that's 6 times e. So 6 times my 2.7-ish number. And that's still fittable on my graph. The e squared, probably not. But this is 16.3 about. So again, these points are plottable. And I generally, if you know me, you know I shy away from using the calculator and tables and such. But the review already wants to hit them with e. I don't know their greater purpose as far as what they'd want to do with that graph, other than to confirm it is what it is, use it in the section that involves e. But 3 questions on review with it, maybe a little bit overkill for me. 2, 0.81 is here, and you can divide that by e, and it just gets a little shorter, right? But the point is, it never reaches 0 once again. It's got a horizontal asymptote on the x-axis, y equals 0, just like that. This is a decay function, as you can tell. It is decreasing. Y is decreasing, trending towards 0 as x increases. It's not negative. It's just decreasing. It's finding its way downward. And there you have it. Number 5. Voilà, le voilà. Number 6. Oh. This is mean. I'm trying to not use a table, and here I can use a table. Honestly, for this one, I'm going to use a table, but I'm going to pull out the table from the calculator. Like, I'm going to construct this in there. It's a little too much for me to say what we're going to do on each number. For one, it's decay, but it's only because this number is negative. There's a vertical stretch, but this thing's going to go that way. This one is exponential decay. And I'll prep my graph. Let's get that one ready. But, y'all, I'm going to the calculator for this one. So, on this one here, let's do y equals 3e to the negative 0.75x. And honestly, I don't remember what I did in the problem set itself. Maybe this is exactly what I did, in which case, awesome. Let's get some of these numbers out like that. These ones look good. This actually kind of now rings a bell. Maybe I did do this at the time, so this might make more sense to do. So I'm just going to copy and paste this table, and then we're going to plot some of these points here for e. Because that 0.75, listen, I can deal with the 3. After all, it's half of the 6. I can just take half of those numbers. But 0.75... First, well, that means a vertical stretch, but also a bit of a horizontal stretch, and also horizontal reflection because it's decay. But let's get these points in here. -2, 13.445, and then -1, 6.351. 0,3. That's the y-intercept. That makes a whole lot of sense. It's that a value. Even when your base is e, even e to the 0 is still 1. but times 3 is 3. And then about 2/3 up. And then around about 1/3 up. And then pretty small. So you're seeing the effects of that graph there. I feel a lot better with the table there. Yes, you can substitute these values in. No, I don't recommend doing it without use of a table, or at least the idea. The number E, if it wasn't an E, I could probably handle it. Because it's an E, not as much. Anyway, hey guys, that's part of section 5.1. I think there are other things I could have explored for 6 questions that would have been more, honestly, that would have been more useful than these ones. At least, you could have had 1 or 2, whatever these, but another couple questions could have been used elsewhere, honestly. All right. Section 5.2, logarithms and logarithmic functions. This was our introduction to logs, which are the inverses of exponential functions. When you take the log of something, the result of that answer is an exponent. It answers the question, the age-old question for us, 2 to what power equals 6. Logarithms can do that. Anyway, so here's what they're going to be doing. They ask you to find the inverse of the function y equals, ln is natural log, the natural log of x minus 2. Natural log is another way of saying log with a base of e. I hope this is not your first time seeing logs. Even if it's the first time seeing it with me, you should have been expressed that this is the same as log base of e, or base e of x minus 2, something like that. So given that e representing the base is even in exponential form, e would be that exact same base. Keep that in mind. When we're finding inverse, that would be right here. This is where you swap x and y, but your goal is to solve for y. Y is buried inside the logarithmic function. To get it out, you must use inverse properties. This one involves exponential function. So one of the properties is that you can raise something to both. You can raise the equal thing as exponents with the same base if you'd like to, like this. And e to the log base e of a number is just that number itself. E to the log base e of y minus 2 is y minus 2, and you have e to the x here. You can also do whatever form of exponential form we talked about. I did mention that your answer to a log question is the exponent. So this exponent sits there. And I did mention that e is the base. E is the base, and the base sits there. So base raised to exponent equals the thing that's inside the logarithm. E to the x equals y minus 2. Add 2 to both sides, you get y equals e to the x plus 2. Now they're doing a double check with the graph. That was not part of their own instruction. So they're just showing you that the natural log of x minus 2 graph is this one in red. When we do graph log functions, we got to note they have vertical asymptotes because they have domain restrictions. You can't take the log of 0. You can't take the log of negatives. The reason for this is because you can't raise a positive number to any power and get a negative or 0. It's impossible. That being said, there are some restrictions on what you can plug in for x inside such an equation that would give you 0 or negative. In this case, if I plugged in 2, or something smaller, 2 minus 2 is 0, anything smaller minus 2 is negative, it's impossible to do. That's why there's a vertical asymptote here at x equals 2 on their graph. Now there's an infinite range, all real number range, but this thing increases in such a way that we'll talk about as we do more in graphs, whereas this exponential function, y equals, well I have it right here, y equals e to the x power plus 2, has a horizontal asymptote because, just what we stated, you can plug in any value for x, but there's no value of x that would ever give me 0 or negative numbers. That being said, you can still plug in any value for x, just your y's are restricted to certain numbers. Y can't ever be 0 or negative, and then you add 2 to it, y can't ever be 2 or less than. Therefore, there's an asymptote at the line y equals 2. This isn't focused on the graphs of these things, but we will be focusing on the graphs of these things, so I want to get that exploration with it. They're giving you a check. Now, what's their check? They're showing you that when you reflect across the line y equals x, these two are the same graphs. Or this is the reflection across the line y equals x to match that graph. And that's what inverse functions do. So when you use a graphing calculator, that's exactly what's happening. All right, let's go ahead. And now I'm not going to double check those with graphs personally, unless they ask me to. And it doesn't look like they are. But they're going to ask us to evaluate the logarithm to begin with, numbers 7, 8, and 9. Let's start with the log base 2 of 8. Now, you can artificially create an equation out of this, set it equal to a variable if you'd like. Take a look at what they have in the example problem, or what I mentioned in the example problem. 2 is the base, x is the exponent. Remember, result of a log equation is the exponent. 2 to the x equals 8. This is what we're asking ourselves. 2 to what power is 8? 8 is 2 cubed, so as these bases match, x would equal 3. Therefore, the log base 2 of 8 is 3. Now, it's probably at the stage that you were taught how to use a calculator to reveal this answer. This is not something you're expected to be able to do in this case, and in fact, it's probably my expectation that there could be a non-calculator version of a test that you take and a calculator version of a test that you take. So you'd still need to know what this is regardless of change of base formula, but we can all but guarantee the answer here is 3. Number 8, log base 6 of 1 over 36. Asking ourselves the same question as we just did on this last one. Log base 6 of 36 asks 1 over 36 asks 6 to what power is 1 over 36? A little bit trickier of a question because that is a fraction answer. Let's start with 6 to what power is 36? That's 2, right? So that's 1 over 6 squared. The real question is, how can I match these bases up? How can I get it, say, 6 to this power equals 6 to this power? I need to turn this into its negative exponent counterpart. 6 to the x equals 6 to the negative second power. Therefore, x is negative 2. And that answers the question. Log base 6 of 1 over 36 is negative 2. You will get some negative exponent answers. You can get negative exponent answers with logs. You just can't take log of negative numbers. Number 9 says log base 5 of 1. Now, the log of 1, regardless of base, will always be the same value, regardless of acceptable bases at least. Can't have base of 0. Log base 5 of 1 is 0. Log of 1 is 0, period. Whether common log, natural log base 5, log base 2, log base 1/3. It's always going to be 0. We're asking 5 to what power gives you 1? Anything to the 0 power is 1. So the log of 1 is 0. Keep those in mind. Okay, numbers 10 through 13. Oh, we do have to graph a log function later. Okay, numbers 10 through 12. Find the inverse of the function. Number 13 is a completely different instruction. So we have to find the inverse of f of x equals 8 to the x power. Like we learned in the last chapter, we'll turn f of x into y, and then we'll swap the x and y. This is the official inverse step here. But we have to solve for y again. Now, as we rewrote some log equations in exponential form, we can also write exponential equations in logarithmic form. If you noticed, 8 is the base, so therefore, we can say log base 8 of, there's something inside here. Even if you don't remember what's inside here, remember what's outside of here on this side of the log equation. The result of a log equation is the exponent. Y is the exponent, this goes here. Therefore, if you were forgetful of other things, that's where the x goes. Now, this was solving for y. We swapped x and y, and we solved for y again. Of course, I tend to use inverse notation, so I'm going to say inverse of f of x equals log base 8 of x. But this is the inverse of this. It seems to hold up. Seems legit. 8 to the x power, log base 8 of x. These are inverses. They reflect across the line y equals x. I think so. Let's go to number 11. You can see number 11 is going to look quite a bit like the example question. So much so that I think I can anticipate the answer is going to be e to the x plus 4. I just think that's it. So let's go ahead and follow that example. Well, I'm going to do my own, but see if it agrees with the example. Y equals natural log of x minus 4. Now I'm going to swap the x and y for our inverse step, and we're going to solve for y all over again. The y is buried inside of this logarithm. So I'm going to rewrite this in exponential form. Now, as an aside, natural log is once again log base e. Whenever we're saying rewrite in exponential form, you say, what's the base? I don't see a base here, Mr. Robinson. This is natural log. Is it a 1? Is it a 10 like the common log? No, it's log base e. Just we write natural log instead. Calculator has natural log. Remember, e is that 2.7-ish number. So if I rewrite in exponential form, I can say base raised to exponent. What's the exponent? Oh yeah, the answer to the log question, x, equals the other guy, y minus 4. Add 4 to both sides. We're going to get e to the x plus 4 equals y, as anticipated. So let's rewrite this in inverse notation, and that's e to the x plus 4. Nothing like being very close to your example problem to start the old day. Number 12, we have y equals log of x plus 9. Notice this one also has a missing base. We're going to get to that. You at home, what is this base? Log of y plus 9 when we swap x and y, take the inverse, got to solve for y all over again. Now this base is log of 10. This is known as the common logarithm. This is the one in your calculator. If you press the log button and then you hit, 100, it's going to ask 10 to what power is 100. That answers 2. So you can try it. It's going to work out. So anyway, rewrite this in exponential form, right? The whole goal is to solve for y. We have to invert logarithms. Exponents do that. So 10 is our base. X is the exponent. Y plus 9 is said result. But we are going to solve for y by subtracting 9. 10 to the x minus 9 equals y. Therefore, the inverse of this function is 10 to the x minus 9 power. That's it. That's all. We are set. Okay, number 13 says graph y equals log base 2 of x plus 1. Now, I do believe that the next section is on graphing, at least for the most part. It's on transformations of log and exponential functions. So all of that will probably be in mind with here's the parent function, here's the new one, graph them such and such. I am going to get started on how I do the tableless graphing with this right here, right now. Because even if you use a table, I don't want you to get frustrated over use of that's another decimal, this is barely increasing, what the heck is going on? And this is actually a pretty decent graph to draw as well. I'm going to tilt this thing sideways. First thing that I do with log graphs, and I mentioned this in the in this portion, so I guess it's good that we spoke on them, is the domain. You can't take logs of 0. You can't take logs of negative numbers. The thing you're taking the log of, which in this case is x, must be greater than 0. That's our domain. Sometimes there's more we have to do to solve for that domain, but in this case, that's it. That means there's a vertical asymptote at the line x equals 0. Remember, these are inverses of, I'll show a second way after, because we just talked about inverses. I forgot that in this section, they sometimes graphed the original function and took its inverse. I'll show you both of those. But exponential functions have horizontal asymptotes. Logs, their inverses have vertical asymptotes. Anyway. As we keep going, the next point I love to plot is where I take the log of 1. You noticed on number 9 that the log of 1 was 0, regardless of base. Log of 1 is 0 even with base of 2. 2 to the 0 power is still 1. So log of 1 is 0, but there's a plus 1. This is our vertical translation. Instead of at 0, we're going to go at 1 when we take log of 1. Plug in 1 for x. Apparently, you get 1 for y instead of 0. From here, this is where, remember, y is the exponent. So y, as every time y increases, that's another exponent up. 2 is that base. You're raising 2 to a higher power here, plus 1, right? 2 to some power plus 1, 2 to some power plus 1, 2 to some power plus 1. And every time y increases the exponent, that's another power of 2 multiplied as your distance from your asymptote. If you know how I graphed exponential functions in the past, then that would make sense. You increase this by 1, you multiply this distance by 2, and you get this number. You increase this by 1, you would multiply this distance again by 2. 2 times 2 is 4. Increase this by 1, 2 times 4 is 8. These are the numbers you want to substitute in for x to get whole numbers out for y. Log base 2 of 2 is 1, plus 1 is 2. Log base 2 of 4 is 2, plus 1 is 3. Log base 2 of 8 is 3, plus 1 is 4. The next power of 2 is 16, and log base 2 of 16 is 4, plus 1 is 5. The plus 1s are already applied to this. That's why I say just keep going up 1 as we multiply by 2. If we're increasing 1 to multiply by 2, we decrease 1 to divide by 2. Take half of 1, half of a half, half of a quarter, etc. And here's your infinite range graph. This goes down forever as it gets closer and closer to x equals 0. Never actually hits it. Goes to negative land when you hit some fractions, numbers that are less than 1, etc. And this goes up forever and ever to the point that I can't reach 32,6, but it has an infinite range. Limited domain, infinite range, there's the graph. Now, in this section when we did things with inverses on them, and it was your first time looking at log functions, let's also take its inverse. Let's practice that one more time if you'd like to. Otherwise, move on to section 5.3. But I can swap x and y. Let's do this all in a different color. Let's use like purple or something. I'm going to swap x and y. I'm going to solve for y again. Now, in this case, I need to get the log equation by itself first before I use that exponential form. So log base 2, or at least it's going to be easier if I do that, of y after subtracting 1 from both sides. 2 is the base, x minus 1 is the exponent, and this equals y like that. So that actually is the inverse. So our inverse equation can be, I'll say inverse, equals 2 to the x minus 1 power. Now, I bring this one up because if you know how to graph this one, you could then graph that equation, the log one, based off the inverse of this. We took its inverse to graph an exponential function you might already know how to do. And then we use that and reflect them across the points y equals x. So as I graph this one, just as an example of what to do, and I'm going to thin it out a little bit, make it a little less transparent. A little more transparent, I think is the phrase. We're going to take this thing here. This has a horizontal translation, 1 unit to the right, has no vertical translation. If k is 0, that means it has a horizontal asymptote on the x-axis on the line y equals 0. There's an invisible 1 multiplying by the 2. This is our, I'm not going to say our y-intercept, but this is our vertical stretch factor. This is the next reference point that I plot, 1 unit up from the asymptote, given my translation. If x is 1, then 2 to the 0, 1 minus 1 is 0, 2 to the 0 is 1, times 1 is 1. When I'm 1 to the right, I go 1 up, and I hit this same point right here that you see. Every time x increases by 1 in my exponent, that's another power of 2 that's multiplied my previous value. When x goes over 1, we double that, and we hit this point. You don't see any points plotted here yet because they're going right after the points we already have, but now here's where you're going to see the change. Over 1 again is another times 2, and you get 4. Over 1 again is another times 2, and you get 8. That should look familiar. That should look like the things we're doing on the other graph, but inverted. Divide by 2, you get 1/2. Divide by 2, you get 1/4 and 1/8, and this kind of thing. Now, this graph was not designed to go as tall as it is to go wide, because I was intent on just using the logarithmic function. However, this is the exponential function for as many points as I could plot. And this should be a reflection across the line y equals x of the logarithmic function. So I wasn't using this just to double check. I was using this to state that you can do problems in this manner, if you so prefer, by graphing what I did in purple and then reflecting those points across the line y equals x. To reflect across these points, you don't have to count, you're just swapping x and y. There's a point here that's 4, 8. Flip it over, 8, 4. There's that point. That's where those come from. So if you know how to graph this one more easily, table or not, you can use those to graph the log ones. I don't recommend it, especially after we do section 5.3, which is coming up next. All right, section 5.3 on transformations of exponential and logarithmic functions. That can include base e and natural log. Let's start with their example, where they say describe the transformation of f of x equals 1/3 to the x power given by g of x equals 1/3 to the x minus 1 power plus 3. Then graph each function. So we're going to do a couple graphs on 14 and 15. Keep in mind this example is pertinent to that. Now, this is where I'm going to, again, be faster with the actual function of the graph on just in a tableless manner. It doesn't matter if it's log or exponential functions, but the transformations will be had as well. The minus 1 inside here is like a minus h. It's a horizontal translation 1 unit to the right, just like I showed at the very end of number 13. And on plus 3, that's a vertical translation, which also means for exponential functions, it's going to be translated not just 3 units up, but so is the horizontal asymptote. And I begin my graph with the asymptote. So you can see this red line is at y equals 3. That's for the g of x equation. So it's a translation 1 unit right and 3 units up from the graph of f. That's the description. And there's the graph itself. Now, the graph has decay because this is a b value that is less than 1. So every time x increases by 1, they're taking 1/3 of what they had before. Now, this is 1 to begin with. Divided by 3 is 1/3, and then 1/9. You divide by 1/3 to go this way, or times 3. So times 3 here is 3. Times 3 again would be 9. Probably can't fit it. This graph does the exact same thing, except it has a translation. So this thing translated 1 unit right, 3 units up. The 1 unit to the right is where you can still go 1 point above because their a value is 1. That's where you have 1/3 to the 0 power, which makes that go away, and there's the 1. Here's the 1/3 of 1 and 1/3 of 1/3, and times 3 is 3, up from the asymptote, not up from the previous point, and another times 3 is 9. Anyway, it's taking that, shifting it, 1 unit up, 3 units right. There's the reference point. There we have it. So let's go to numbers 14 and 15. 14 does jump us into not only an e function, but also with a horizontal shrink by quite a bit. It's once again one of the things where I not only stated, why did we do so many e graphs in the review of section 5.1, sorry book, but now we're doing another one, and it's yet an infuriating kind of set of values. A horizontal shrink by a factor of 5. I'm not going to change my scale on my graph. So for this one, I am going to be using l'étal graph because we have to go l'étal. Now, the original one isn't quite the parent function. It is a decay version of E, but we can still state that. The graph of G is what compared to the graph of F. It has the 5 inside there with the x multiplying by it, which means we need our x's to be a fifth the size that they were before. It's a horizontal shrink by a factor of 1/5. And not negative 1/5. There's no reflection to be had outside of what was originally there. It's followed by a translation 8 units down, which is good. I'm glad it's not 8 units up. At least then we can see some of our points we're going to be graphing. Let's start with the e to the x graph. Like I said, I'm going to go without a table basically here. I'm going to do this one in blue and this one in green. In blue, we're going to have a horizontal asymptote on the x-axis, y equals 0. E to the 0 power, like anything, is 1. When we increase x by 1, we're going to be dividing by e instead of multiplying. Dividing by e is going to be around that 0.37 value. As we divide by 1 over e, we multiply by e. So 1 times e is around 2.7. So there we go. Times e is around 7.4. We saw these values a bit ago in section 5.1, so I'm leaving them. And then times another e would be around 20.1. This is 17, 18, 19, 20.1 probably up there. Quite out of reach, quite tall, but there's the idea of that graph, so I'm going to still try and get that plotted. That's the original f of x function there. I'm a little bit above it, I think, but I tried. And that's all that matters, right? We just try, yeah? And then we put a 0 there randomly. I was trying to arrow this thing down just 1. Or left. There we go. Let's pretend like that's it. All right. Now the g of x equation is going to be translated 8 units downward. I tend to do the translation first, even if I say followed by, because I know what I'm going to be doing with my stretches and shrinks with respect to this. It doesn't translate at all left and right. The a value in front is still 1. I plug in 0 to get 1 up from here at -7 still. No change. The change is actually now just in horizontal shrinkage. Now, in horizontal shrinkage, that means that I am still going to get up to 2.7 and 7.4 up from the asymptote, but it's going to be a fifth the size as it was before, so it's going to be very skinny. If I go a fifth of the way over, that's when I divide by e and get my 0.37-ish value, so it's right there. It's very tight, just a fifth of the way over toward 1. Go -1/5 over this way. This is where you get your 2.7 value. So like I said, it's an extremely tight push. Not much I can fit here. 7.4 units up from -8 is going to be right below 0, and that's when I'm 2/5 up, so that's right there. And then I can at least hit the 20.1 up from -8 to be at about 12.1, and that's 3/5 of the way over. So this is clearly just going to be a super tall graph. Oh, 20.1. 3/5 of the way over like that. So you're barely going to see anything other than a vertical line on this one here, guys. That's where I kind of have beef with this and going like, you want me to graph this, right? Like, you want it to be presentable to the masses, yeah? And I'm not giving you the table, but I'm giving you the idea of the effects of a horizontal shrink. Now, it does go toward -8. It doesn't ever hit it. It flattens out, as an asymptote would. And there is that graph on number 14. So quite the ordeal. I hope you followed along. If there's anything we could do is change scale. Should have I? Probably. And that's the end of my sentence. I don't know what else I want to say there. Number 15. Number 15. We have f of x equals log base 4 of x. And g of x equals 1/2 times log base 4 of x plus 5. Okay. Quite a bit to talk about with this one. Let's first just describe the transformations, then we'll get into the graphing. As far as the description goes, the graph of g is a vertical compression, vertical shrink, by a factor of 1/2, followed by a translation, 5 units left. The x plus 5 inside gives you that one. Now, that was good then. Now, we first will graph f of x. Then we'll do the g of x afterward. Like I said, I want to do this one a little bit faster this time. This domain is x is greater than 0, as it would have been from the previous one that we graphed the log function on. Can't take logs of 0 or negatives, so this f of x graph kind of starts here-esque. I also want to take the log of 1. Log base 4 of 1 is 0, just like any other base, so I can get a point right there. 1 away from my asymptote. Every time x or y increases by 1, my exponent, I can multiply another 4, that's my base, distance from my asymptote. Increase by 1, multiply by 4. Increase by 1, multiply by 4. 4 times 4 is 16. It goes yay far out. Yay! You decrease by 1, we divide by 4. Kind of sounds opposite of the exponential functions, right? I sure hope so. We didn't get to do a conventional exponential function one. We had to do e to a power. So sorry that we didn't get to talk about 3s or 2s or anything like that so much. Actually, no. On the last problem, I did take its inverse and do the doubling effect, but it was still not its own problem. All right, there's the parent function. There's my f of x equation. Not a good looking curve from that, but it has an infinite range. G of x equation takes this stuff and vertically compresses, and it goes 5 units to the left. Now, why does it do 5 units to the left? Well, for domain's sake, x plus 5 now has to be greater than 0. It's whatever you're taking the log of that must be greater than 0. In this case, it's x plus 5. So x must be greater than negative 5. Therefore, the vertical asymptote is on the line x equals negative 5. That is the 5 to the left. I'll deal with the compression in a bit. The log of 1 is 0. Now, when I plot this one, I want to keep a couple things in mind. This is not x equals 1. This is x equals negative 4. How far away is negative 4 from my asymptote, though? 1 away. Why does that matter? Because negative 4 plus 5 is 1. You are taking the log of 1 when you plug in negative 4 for x. So 1 away from here, given no stretches or compressions horizontally. 1 away from here, you're taking the log of 1, you get 0. No translations here, by the way. We're not doing plus or minus this like we did last time. Every time your exponent increases by 1, we're going to do another multiplier of 4. But keep in mind, because everything's about to be halved, that includes your exponents. Your exponent gets halved, vertically compressed, so we go up a half before we multiply by 4. 1/2 and times 4. That's 4 away from the asymptote, not the previous point. Up another 1/2 to go another times 4, which is 16 away from negative 5, which is in this case 11. And I can't fit 64 away, so that's all I can do that way. You go down a half to divide this by 4 to get a quarter, and down another half to get 1/16, pretending like I can actually get 1/16. That was actually a very bad representation of 1/16. I apologize. But there's going to be this graph here. It also has an infinite range, of course, but it is vertically compressed compared to the other one. It's a little bit over, so we can get some of those points. And there is this graph. So f of x, g of x, we're all taken care of. Okay, about 45 minutes in here. Let's go to numbers 16 and 17 to write a rule for g based off these descriptions. We are not graphing. On number 16, we are taking, of course it's e to the x, but this part doesn't matter what the base is. It can be whatever it wants. We're taking f of x equals e to the x. We're going to vertically stretch it by a factor of 3. We're going to translate 6 units left and 3 units up. Sorry, 6 units left and 3 units up. Okay. Let's begin with the verticals. Well, we can probably do this all in one step here, but the g of x is going to take your f of x where you vertically stretch it by a factor of 3, like so. There's the function. Inside the function, we got to go 6 left. That means there's a reversal of here. And then up 3 follows all this. Remember, this up 3 is not affected by the times 3. Even the plus 6 isn't affected by the times 3. The everything that's inside here gets affected, but in its own way. We're all good. Order of operations is intact. This becomes 3 times e to the x plus 6 replaces x, so x plus 6 power, and then plus 3 on the outside of that. So this is that function with those things in mind. No graph. Again, didn't matter if it was e or 2 or whatever. That's just how it works. Number 17, let the graph of g be a translation 2 units down, followed by a reflection in the y-axis of the graph of f of x equals log of x. Once again, something that's a vertical translation with then a horizontal reflection. Y-axis is a horizontal reflection. They can be done in the same step. I know some people aren't comfortable in doing that, not sure when you can or when you can't. I'll say in this case you can. In this case, we are translating 2 units down. That means whatever we're taking the log of inside here, the 2 units down is outside of here, regardless of what's inside there. So whatever's inside here can still happen. Translations or reflections. Reflecting this is log of negative x, and it looks like that. Now, there's nothing else I can do. Oh, let me write the version that says f of x before that. So f of negative x minus 2, like that. And then we get to this right here, log of negative x minus 2. There's nothing I can do here to simplify it more. This can't become the negative log of x. These are two different things completely. This graph actually goes over to the left like that, whereas a negative log of x would have gone downward like that. So they're two completely opposite graphs. So there's the translation, there's a reflection in the y-axis. We're all good. All right, let's move to section 5.4 on properties of logarithms. This is where we start to hit expanding and condensing. Looks like some other evaluations to be had. Oh, and change of base. Change of base will also happen. So on parts A and B of the examples, expanding natural log of 12x to the fifth over y, we're taking a couple properties here. There's something called the quotient property and product property, and something called the power property. They're probably easy names. I don't tend to call them that. I don't call them anything. But what I say in these cases is we're taking the log of, right now we're talking about the quotient. The log of a quotient where 12x to the fifth is dividing by y inside of your natural log. This can be rewritten as two separate logs provided that you subtract them. I want to remind you that logarithms are exponents. When you take a logarithm, you get an exponent. So this is an exponent minus an exponent, which seems to make sense. When you would divide two values that had exponents, you would take the base and subtract those exponents. Take this base of e and subtract these exponents here. All good to go. Same with product property. 12 is multiplying with x to the fifth power, so we can separate those as two separate logs through expansion, where you add those two exponents as you would for two values of the same base when multiplied. As these are multiplied, you keep the base and you add the exponents, right? These are exponents here. So now it's this plus this minus this, all in their own natural log state. The last one's power property. Keep in mind, when you take the log of something, you get an exponent. So if I have an exponent inside my log function, that result is an exponent. This is an exponent times an exponent. But why does the exponent need to be inside there? It doesn't. So you can take the exponent, take it out of its log, and multiply it by that log value. This is what's considered to be full expansion of this set. And this is used for different reasons. In this particular problem, I couldn't tell you exactly what benefit it would serve right off the bat, but they have their own specific reasons for different things depending on what it is. Now, the next one, part B, says evaluate log base 4 of 36 using natural logarithms. This asks you 4 to what power is 36, and I couldn't tell you what it is. I don't know. It's not 9, that's 4 times 9. It's somewhere between 4 squared and 4 cubed. 4 squared is 16, 4 cubed is 64. But if you ever wanted the answer, you can use your calculator and the change of base formula. Change of base formula takes the log of the thing you're taking the log of, like log of 36, and dividing it by the log of the base. So log of 36 divided by log of 4. They said use natural logarithms, so you could take natural log of 36 divided by natural log of 4. You'll get the same answer as you would get if you took log of 6 over log of 4. To remind you, your calculator has these two functions. They have log here, and they have natural log here. Log is common log, that is base 10. So they did natural log of 36 over natural log of 4. We could also, although they said use natural logs, but this would also work, log of 36 divided by log of 4. As long as they have the same base on top and bottom, you'll get the same answer through that division. And this is your change of base. Remember when I said the answer would be somewhere between 2 and 3? This is it. So they round to a few decimal places, and they get 2.585 about. And that's what we're going to be able to do for these problems. Oh, speaking of which, let's go back. Remember when we were doing log base 2 of 8 at the time? We actually did that on a problem. Remember how that was 3? That's log of 8 over log of 2. 3. So it works. Okay. Let's jump to the problem set. We have 18 through 23 where we do expanding or condensing. Now, we didn't do a condensed problem in the examples. We actually start with 3 on expansion. We'll do condensing afterward. Expanding means take these into their own separate logs and take everything out of the logs that you can. Condensing means pack everything into a single log. Put everything into the log that you can. So to expand this one, we have log base 8 of 3xy. This is a product, 3 times x times y. So the log of a product equals the sum of these 3 separate logs. Log base 8 of 3 plus log base 8 of x plus log base 8 of y. That's it. There are times where I try and evaluate ones with numbers, like log base 8 of 3. That's not a clean number, though, so I'm going to leave it. Number 19. Log of 10x cubed y. Once again, it's a product. Notice how I wrap this part around parentheses always. I think it's helpful. It's a product, so we can separate this into 3. Remember, 10x cubed is 10 times x cubed. So this is log of 10 plus log of x cubed. And only the x is cubed. This is important for our next step. Plus log of y. Okay. Now for this, a couple things. One, I just spoke on evaluation. 8 to what power is 3? I don't know. Log is common log. That is 10 as its base. 10 to what power is 10? That number is 1. If I can evaluate it, I will. So this turns into a 1. Log of x cubed, this isn't about the base anymore, just about having an exponent inside the log. This can come out and multiply by this thing. This is 3 times log of x. Again, pull out anything that you can, in this case, the 3. And plus log of y. This is full expansion of this problem and evaluation, if you will, simplification. There we have it. Number 20, we have natural log of 3y over x to the 5th. This is going to be a lot like the example problem that we had. Okay, so we do have a product on top. We have 3 times y, so I can separate that into natural log of 3 plus natural log of y. We are dividing the x to the 5th, so that'll result in the subtraction of those exponents. So we subtract x to the 5th, natural log of x to the 5th, from those other two. I can't evaluate these further, but this 5 can pull out in front of this natural log just like it did in the other problem. So this will be natural log of 3 plus natural log of y minus 5 times the natural log of x. So like I said, it's a lot like the example problem, but just with kind of shuffling around of numbers and such. All right, the next 3 are condensing. You can see there are multiple logs and everything is pulled out as much as possible. So now we're going to try to bring things in more. Do the opposite of what we did for the 3 properties that you see. Quotient, product, and power property all have, you have the sum of 2 logs, multiply them. You have the difference of 2 logs, divide them. You have something multiplied in front of the log, put it in as an exponent. That's the kind of thing we're going to do here. So number 21, we have 3 times log base 7 of 4 plus log base 7 of 6. One of the things that needs to happen, and it will, these logs need to be the same base. Just like when we write these ones out, they need to all be log of that base that you started with. So these all need to be log base 7 when we contract them, condense them. Before I do any condensing, I'd love to deal with this 3 first as it only applies to this log. Therefore, I want to turn this into log base 7 of 4 to the 3rd power. That's part of the condensing acts. That's the reverse of the power property. Nothing yet to do with the log base 7 of 6 until we take care of that portion. So 4 cubed is 64. I'd love to turn that into a 64. And I'd love to write these now as one single log. As they're adding as separate logs, we will now write them as a single log and the product of these two numbers here, 64 times 6. And of course, if there's any evaluation to be had, let's go for it. 64 times 6 is 384. So log base 7 of 384, not a clean number. We're going to leave it like that. There's the condensing of that problem. Number 22 is log base 2 of 12 minus 2 times log base 2 of x. Same thing applies to this one as it did for the previous one. That 2, let's go ahead and bring it all up in there. You don't have to make it the -2, otherwise you turn this into a plus and then it kind of gives you more steps than you need. So let's still keep this as a minus, given that a 2 goes up inside there and as the exponent. Because it's a subtraction of these 2 exponents, right, that's what logs are, that results in the division of these 2 inside of a single log. We're taking the log base 2 of 12 over x squared, and that's all that can be done with it. So we are done with it. And then number 23, and again, none of these problems, maybe just this one with the 1 inside of there, none of these problems have done more for you than not regarding why would we do this, what help does it give us. I'll tell you what, the condensing doesn't just do things regarding evaluation to help you. It helps us solve log equations. When we hit section 5.5, condensing to a single log is one of the required steps to do before you can convert it, say, to exponential form. So it does definitely serve its purpose, and the expansion does in some other cases. Let's start with the condensing of the power using the power property. This will be natural log of x squared plus natural log of 2 to the 5th. I'll turn that into 32 in a bit, minus natural log of 8. So you're going to see a condensing act here that will also serve a little bit of benefit. Give this a second while I do so. This becomes the natural log of, because these two are, it's not just about adding, these two are positive. See, if this was negative right here, then these two aren't positive, right? Doesn't matter that you show addition. But because these two are positive, these two multiply together. 2 to the 5th, which is 32, multiplies with x squared. And then this one's negative, therefore it goes in the denominator. We divide by 8, all inside a single natural log. Now 32 over 8 is 4. So there's a little bit of reduction that's had there. That's natural log of 4x squared. We can do that. We did do that. We shall do that. We must do that. There's your result. All right, let's go to numbers 24 to 26. Use the change of base formula to evaluate the logarithm. This is a logarithm. This is all in a calculator-based way. Log base 2 of 10. You have one of two options. You can either write this as the log of 10 over the log of 2. I prefer that one. Or natural log of 10 over natural log of 2. You'll get the same result regardless. The reason I prefer this one isn't because I wrote log. It's because 10 is here, and log means common log. Therefore, when I write this one, this is also, log base 10 of 10 is 1. This is also 1 over log of 2. If that helps clean something up. Now, that doesn't help answer the question. We still have to use the calculator. But I just wanted to remind you that log of 10, folks, is 1. Whereas natural log of 10 ain't 1. But if you did division of 1 by the other, regardless of what you do, you'll still be good. Anyway, if I do log of 10 over log of 2, or 1 over log of 2, I'm going to get this answer. This is the answer to our question. If I did natural log of 10 over natural log of 2, I should still get the same answer. Now, I'm not going to do the same thing twice each time like this. I'm just reminding you that either or works. They didn't force one on us, so we did that. And I'd love to kind of, not double check this answer, but make sure that this answer makes sense to me. So this answer was around 3.322. Couple threes, couple twos. Does the answer make sense? Yes. It asks 2 to what power is 10? 2 cubed is 8. 2 to the 4th is 16. To be between 3 and 4 makes sense to me. You can double check it, try and plug it in, but I'm going to trust it for everything we did. Number 25 says log base 7 of 9. We're asking 7 to what power is 9? This will be an answer somewhere between 1 and 2, significantly closer to 1, I'd say, because 7 squared is 49. That's a little further out, right? So log base 7 of 9. Here, let's do natural log. Let's say natural log this time. Natural log of 9 over natural log of 7. And it needs to be in that order. I'm not going to show on the calculator. I'll just type it out and see what we get. If I type it correctly. Natural log of 7. And I'm getting around 1.129. Like I said, somewhere between 1 and 2. Significantly closer to 1. I believe it. I'm going with it. Number 26. Last one in this section. We have log base 23 of 42. Interesting set of numbers. Don't really know what to say on them other than I expect a number close to 1 again. What's 23 squared? I don't know. 529, I think. Might be 529. Anyway, 23 to the first power is 23. 23 squared, I think, is 529. This will be between 0 and 1. Or 1 and 2. Between 1 and 2. And much closer to 1, again, I'd say. But as long as we get an answer like that, right? So log of 42 divided by log of 23, or natural logs, but they got to be the same no matter what you do. 1.192. Very close to 1.129. Okay, there we have it. All right, section 5.5 on solving exponential and logarithmic equations. Now, there are different actions depending on what your setup is, but it remains the same that if you have, well, there are a couple things we can talk about. For one, on exponential functions, your goal is to probably try and match your bases. If you can get the bases equal, you can set the exponents equal to each other and solve. There is no restriction on our x's, no extraneous solutions with exponential functions. You can have an infinite domain, all real number domain. For exponential functions where you can't match the bases, you want to use logarithms to solve. That's the whole idea of logarithms. They're the answers to exponential functions in question. So I'm sure we're going to run into those. I haven't looked at the problems yet, but I'm just saying that. Logarithmic equations, if you have logs on both sides of the equation with the same base, you can set the insides equal to each other. But here's where you might want to just make sure that you're never taking the log of a negative number. So substitute those in. If you can, otherwise, if you have a single log in your equation, get it by itself on its own side of the equation, rewrite in exponential form and solve. Or if you have multiple logs in the equation, condense into a single log before you do either of those two actions. You still have to double check those answers with condensing because you might turn something into a quadratic or something that wasn't originally before. Let's take a look at this example question. They have natural log on both sides. That means they have matching bases. This is the property of equality for logarithmic equations. If the left side and the right side have matching bases, you can set the insides equal to each other. The only way that this is possible, natural log of this equals natural log of that, is if this equals that. So we solve for x conventionally. You get x equals 15. They say double check, which is fine. 15 times 3 minus 9 is positive. I'm not making sure they're the same number. I'm good on that. I'm making sure they're both positives, which, unless they botch the problem, is it. Now, that's the only example that they show. There are a lot more they could have shown, but let's go ahead and proceed forward. On number 27, we have 5 to the x power equals 8, and automatically I'm stating here, well, I cannot match bases here. 8 is 2 to some powers, 8 to some powers, 5 is 5 to some powers. I can't do that. What I can do is I can log both sides, and I'd like to log them with base of 5 because 5 is the base that contains my exponent. When I do that, we exercise a couple properties in mind. It's up to how you want to state this. Number one, the x can pull out and multiply in front. This is a bit of an intermediate step that I won't write after this problem. Number two, the log base 5 of 5 is 1. 5 to what power is 5? It's 1. So x times 1 is just x. So here on out, when you see this is another property involved. Log base b of b is 1. Therefore, that part will kind of go away. X will come out. As a result, that's why we're doing that logarithm. So x equals the log base 5 of 8. That's the exact answer. Of course, we probably want to approximate this one. And in doing so, we're of course going to do the log of 8 over the log of 5, as we saw previously. So a number between 1 and 2 is expected. And we get 1.292 about. And there's the solution for x. That answers the question 5 to what power is 8? There it is. Number 28 is a log question. Log base 3 of 2x minus 5 equals 2. So this is one that is already, well, the log is already by itself. We've done things where we've rewritten log equations in exponential form. We would rewrite this as 3 to the second power equals 2x minus 5. Let me show you an alternative to this that will be better for the inequality problems we have below, which, by the way, was not something they did in one of the examples. You could also do this, raise these as exponents with 3 as the base, because 3 to the log base 3 of something is just that something, and you can see here 3 squared, which is over there. So this is the other canceling out effect when you have a log and use an exponent form in that. There's a canceling out effect that brings that there. And like I said, you might want to use that for the inequality step, just so you know which way the greater than and less than is supposed to face. Anyway, 3 squared is 9. You get 9 equals 2x minus 5. Add 5 to both sides. Divide both sides by 2. You get x equals 7. Why not? Does it work? Yes. I don't need to double check that one. If this one equaled a number as a result anyway, that will work out just fine. Number 29 probably needs to check for extraneous solutions because of its nature, which is multiple logarithms separated that will condense into a single one and will change the nature of what these original logarithms were. These first started as linear quantities inside of each log function. We're now going to condense this, and by condensing this, I mean the sum of two logs equals the log of this product, x times x plus 2. As we can mosey on forward here, this is natural log of x squared plus 2x. What we did was we took two individual log functions with linear quantities, and now we turn it into a single log with a quadratic. Quadratics have two solutions. Sometimes those solutions will be something that won't work for the original ones because we can't take log of 0 or negative. This might have extraneous solutions, but we're not done. Remember, natural log is log base e. That means this is rewritten as e to the third power. E to the third power equals x squared plus 2x. This ain't just any old quadratic equation. This is one that we got to solve using either quadratic formula or completing the square. Now, I prefer completing the square for a situation when I have a 1x squared and an even linear coefficient. So I'm going to do that. If you'd like to solve using quadratic formula, be my guest. This number is going to be a 1. This number is going to be a 1 by completing the square method. This factors to x plus 1 quantity squared. And to solve, we'll take the square root of both sides, and we will subtract 1 from both sides. So x plus 1 equals plus or minus the square root of e cubed minus, or plus 1. Subtract 1 from both sides. To solve for x, we get x equals negative 1 plus or minus the square root of e cubed plus 1. Hardly the kind of answer that we want to see here. So we are going to do negative 1 plus the square root of e cubed plus 1, and negative 1 minus the square root of e cubed plus 1. So let's go to the calculator. Let's check them out. Negative 1 plus square root of e cubed plus 1. So there's this guy. And then, so 3.592 about, and then negative 1 minus. Negative 5.592. 3.592. Negative 5.592. Okay, so with these two answers here, we do have to double check and see if any of these may be extraneous. You go back to the original equation and ask yourself, if I substitute these, am I taking the log of 0 or negatives ever? Not this one. These would have turned positive because of the squared bit. It's this part that matters. Natural log of 3.592 is good, and 3.592 plus 2 is good. Those are positive. The negative 5.592 is the problem. Log of a negative, log of a negative. Even if one of them was positive, if the other's negative, it's a problem. This is an extraneous solution. Therefore, your only solution is this one, the negative 1 plus the square root of e cubed plus 1, not the minus. Different answer, but that's what comes to be. Good question. Numbers 30 to 32, we are solving inequalities. Now, they're just like solving equations. We'll have a couple caveats in mind just in case. We begin with 6 to the x power equals, or is greater than 12. Same like number 27, I would like to log both sides with 6 as my base. This will bring me to just an x on this side. Log by 6 of 12 is I don't know what, and that's what our goal is. Figure out what that thing is with the calculator. And that'll tell me what x is greater than. Now, I don't know how to use a greater than symbol and say approximately greater than. So when I say greater than, please understand this is a rounded answer. I'm going to type in natural log of 12 over natural log of 6 on my calculator. And I'm getting 1.387 about. So x is greater than, x must be greater than 1.387. All right, number 31. Number 31 is a logarithmic inequality, and this one is going to have a couple of differences involved for us. First of all, when it comes to getting x out of this logarithm, this is where I do recommend that you don't, we're going to rewrite an exponential form, but not by straight conversion. I would actually do it with e as my base so that you know exactly which side these things are on. Why am I doing e? Because it's a natural log. E to the natural log of something is just that something. Here we're going to be left with x. Now on this side we have e to the 9th, but notice that you know which side this inequality goes on, so it's probably best you use the function that way. So x is less than or equal to e to the 9th. I don't know what e to the 9th is, so we'll figure that out. It's going to be around 8,103.084. I don't know to what number we want to round. So as a final, we'll have 8103.084-ish, whatever. There's another caveat to this, though, and it's because we're talking about logarithms. Remember, we cannot take logarithms of 0 or negative, and we're asking what values here satisfy this inequality. Less than or equal to this will satisfy it, but we can't take log of 0 or negative. So domain x has to be greater than 0 means as we go less than this number, this would hit 0 and negatives if we kept going, so we must restrict this to 0 on this side. This is the full compound inequality solution set that satisfies this inequality. Number 32 is back to an exponential, so I must stress here that we have an all real number domain. There is no positive, negative restriction on this. This just is whatever it becomes when we solve it. So this is e to the 4x minus 2 power is greater than or equal to 16. If you want to log both sides immediately and cancel out whatever's there, you should natural log both sides because this has a base of e. So this leaves you with 4x minus 2 on this side. And on this side, we have natural log of 16. I'm going to leave it as natural log of 16 until our final answer. I will add 2 to both sides and divide both sides by 4. So plus 2 divided by 4, x is greater than or equal to natural log of 16 plus 2, all divided by 4. There's an exacto answer. We didn't divide by a negative, but if you do divide by a negative, the inequality flips. That's something to remind you of. If I go to the calculator for this one, I do want to open this up with parentheses here before I hit natural log of 16. Close that parenthesis for the natural log, then plus 2. Close that up for the numerator, all divided by 4. And we're getting 1.193. So x has to be greater than or equal to 1.193. And no restrictions there. We're all good to go. Looks great. And that is a lot of section 5.5. Pretty good questions. There are others that could have been involved. There were no matching base ones here. I think that's why it was good that I stressed the importance of, even though we only did it like a couple times, on the very first questions, not the very first, where were they? Was it on this review? I thought there was a question where we did some matching bases. I have no idea what I'm talking about anymore. I could have sworn that we did match base problems. Oh, right here. This log stuff right here, and I said 2 to the x is 2 cubed, right? Rewrite it as 2 cubed. This one, match the base. Those kinds of things will be involved in greater detail because you got to use more power properties, exponential properties, and they weren't fully used here. I just want to remind you that that's possible. Otherwise, you can solve using logs if you can use the calculator. All right, last section is section 5.6. This is on modeling with exponential and logarithmic functions. The section itself was tons of fun, am I right? Especially when we hit that last set. These first questions right here ain't bad, and they have an example that are like this to resemble it. Write an exponential function y equals ab to the x whose graph passes through 1, 3, and 4, 24. Your goal is to come up with this y equals ab to the x by finding a and b. You have a couple xy values, xy and xy. You can substitute into this equation type to model a system of equations. And then we solve using one of two methods, substitution or elimination. The book uses substitution. I'll use substitution for at least one or two problems and elimination for the other ones. So with substitution, they get a by itself. A is always going to be to the first power in either equation. They tend to use the smaller equation, I'd agree. So they divide both sides by b. They get a equals 3 over b. If you substitute 3 over b in for a in the other equation, you can then come up with an equation with only b's in it. B to the fourth over b is b cubed, so you have 3b cubed on this side equals 24. Divide by 3, take the cube root, you get b equals 2. I want to remind you that even if it was a square root, we wouldn't say plus or minus the result because you can't have negative b values. You can't have negative, 0, or 1. Only positive. So even if it was a square root, we just get the positive result. B is 2. We already have an equation with a in it, which is 3 over b, and 3 over 2 should be your a value. Therefore, we can make a full equation of that. Y equals 3 halves times 2 to the x power, or 1.5 times 2 to the x power. And that's the result. Now, there are other things I could say on it with regard to logic of this, if this process doesn't make sense. With regard to graphing, how the y-intercept thing holds up with a, how that growth factor applies, how it's like geometric sequences. There are a lot of different things I could mention. Like on this one, I could tell you this answer straight up based on knowledge. Let's talk conventionally about this just so you get a basic understanding of what's happening. Exponential functions are ones where each time x increases by 1, you're multiplying another set of your growth factor, your b value, or decay factor if it's less than 1. This goes from 1 to 2 as x, so as the exponent increases by 1, we go from 12 to 24. We're multiplying by 2. I can tell you guys right now the b value is 2. The a value is your y-intercept value, y when x equals 0. That's 1 away from 1. If I'm multiplying by 2 as x increases, I'm dividing by 2 as x decreases. A is going to be 12 divided by 2, which is 6. I can already tell you the equation is going to be 6 times 2 to the x power. There is logic in this stuff that can be applied, but let's do this with their methods. Y equals ab to the x power means substitute this for y, this for x, this for y, this for x in their own sets of equations. As a rewrite of this equation with a by itself, I can divide by b, I get 12 over b, and I can use that and substitute it in for a in this equation down here, so I can get an equation with just b's in it. 12 over b times b squared. B squared over b is b. And you're left with 24 equals 12b. Divide by 12, you get b equals 2. all of this stuff is using what we needed to use in this. The expression of A that represents how B is, blah, 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 blah. 12 times what number is 24 is what we had to ask, right? That was the big thing because they were just separated by 1 power of your B value. So B is 2, A is 12 over 2. Well, why is A 12 over 2? Because we are just but 1 power away from our y-intercept when x equals 0. 12 over 2 is 6. And hey, that looks like the same equation we're going to write as was above, 6 times 2 to the x power. That was the substitution method, or like I said, using a little bit of logic, and there's the answer to 33. Number 34, I'm going to go ahead and use a different method called elimination. And again, any process is yours up to what you want to do. I could probably give you this answer as well. I'm going to try this one mentally first just to get the idea in mind and saying, hey, there are other ways if you work it out. I'm not doing elimination method mentally. I'm using the idea of what we have to do for this problem. I'm going to say y equals 64 times 1/2 to the x power. Okay. So here's an answer to look forward to. Whee! Let's go ahead and see if that's what we can get. As far as elimination method goes, that'll be reserved for the same substitution. Now, in this case, I probably want to place the bigger x on top here. So with y being this number, 2 equals ab to the 5th power, and then 8 equals ab cubed. This is only because through elimination method, we're going to divide these two equations. They're aligned in such a way that things will clean up the way that we want them to, where a divided by a is 1, b to the 5th over b cubed is b to the positive 2nd power, that's what I wanted, and 2 over 8 is a quota. We will take the square root of both sides, and like I stated, you will not do plus or minus here, it's just this. Square root of 1 is 1, square root of 4 is 2, b equals 1/2. Hey, we've said that before. Now, the one thing elimination method doesn't do that the other method does is it gets a by itself immediately. This one does not have a by itself. So let's take one of the equations, maybe the smaller of the values, and we'll say 8 equals a times 1/2 cubed. 1/2 cubed is 1/8, so 8 equals 1/8 times a. Multiply both sides by 8 to solve this. 8 times 8 is 64. A equals 64. Hey, we got that number there. So this becomes y equals 64 times 1/2 to the x power. Now, before you believe that, oh, he just has an answer key right here. Oh, he's done these problems before. Oh, whatever else. No. From 3 to 5 are 2 powers of x. We divided by 4 in total to get here. That means we divided by 2 twice. That's multiplying by 1/2. That's our b value. If we're dividing by 2 going to the right, we're multiplying by 2 going to the left. So I have to go from 3 to 2 to 1 to 0. That's times 2 is 16, times 2 is 32, times 2 is 64. That's where we're getting our y-intercept. So that's what I did in my head, just to make sure you have an idea of that. Now, not all problems are done that way that will help you best. For example, when I do this problem here, it's probably not best I do that, although I think I can see what the effect is regardless. Number 35. So I would like to try this one more time in my head, and I'll use substitution method for you again afterward. Let me explain in my head what I'm seeing. This is just happenstance that this is working out, right? From 4 to 1 are 3 powers of your b value away. We must be dividing or multiplying by something, whatever. It looks like if you divide by 5, it works out. If you divide by 5, you get 5. That's once. That's when x equals 3. Divide by 5, you get 1. That's when x equals 2. Divide by 5 again, you get 0.2. That's when x equals, or 2, and that's when x equals 1. So it looks like your b value is 1/5. Your a values, if you divide this one by 2, 0.2 divided by that is 0.04. So I believe this equation is y equals 0.04 times 1/5 or 0.2 to the x power. Whichever one you want to write, it's up to you. This is kind of how my final is going to look here. So, whoops. Put that in blue. Let's use substitution and figure that out. I keep bringing that stuff up because I don't want you to live in process too much. I want you to have something that works. That won't always work for me. I love the substitution process. It's fine. Y equals a b to the x power. Y equals a b to the x power. That's a 1. You can rewrite this equation as a equals 0.2 over b. It's kind of weird to look at that. Remember, 0.2 is 1/5. So if you want to write these, remember, by the way, you can write these as decimals or fractions. That's going to be your call. You know what? This wouldn't be 0.2 because we're going from 1 to 4. We're increasing. So I made a mistake on that. That would actually be 5. We're actually multiplying by 5, right? Because that's going backwards. The fact that they're written backwards, I guess, threw me for a loop. So that would actually be a positive 5, not or sorry, that would be a 5, not a 1 over 5. The 0.4 would still be 0.4. But, okay, that's going to go that direction. Anyway, what I was going to say is you can write these as fractions or not. That's your call. But I'll leave it as 0.2 for now. Anyway, so substitute into the other equation, right? That's how you solve systems with these things. So 25 equals 0.2 over b times b to the fourth. B divided by b, or b to the fourth divided by b is b cubed. So 25 equals 0.2 times b cubed. At this point, yeah, you could divide by 0.2. That's the same thing as times 5. So kind of your call, but I'll write divided by 0.2, and I will do times 5. That's b cubed equals 125, or b equals les 5. So, okay, it is going to be 5 there. My bad, I was going backwards and dividing all that. We're going this way, multiplying by 5, right? All right, so b equals 5, and what's a? Well, a is that 0.2 over 5 that I was talking about. So 20 over 5 is 4. 2 over 5 is 0.4. 0.2 over 5 is 0.04. That's where I was getting that number. So y equals 0.04 times 5 to the x power is the answer. 0.04 is also 1/25th. If you want to write the fraction, 1/25th. All right, one more question to go, guys. Number 36. A shoe store sells a new type of basketball shoe. The table shows the pairs S sold S over time T in weeks. Use a graphing calculator to find a logarithmic model of the form S equals A plus B times natural log of T. They should really keep that all in one line. A plus B times natural log of T. That represents the data. Estimate how many pairs of shoes are sold after 6 weeks. So I'm yesing this as opposed to trying to come up with my own model with the natural log stuff. Now, if you have more things to study in this section, there are a lot more types of problems that you're going to have to do than just these ones. These are the ones that I expected them to have more of. So I'm glad it's in the review, selfishly. I'm sure the chapter test or cumulative assessment or something is going to have me do some of the other type. But I would explore some of the other ones if you got to do more than just the solving ones here and the ways you have to write models. But if we get to use the calculator we get to use. So let's go to there and let's turn this thing on. I had a table and I intend on using it. We have T as 1, 3, 5, 7, 9, and pairs sold are based off that T, which is 5, 32, 48, 58, and 65. 65. Now, they said use natural log. So there's a natural log regression model that we're going to use for this. So when I go back to the calculator, I will go to stat and find natural log regression. We'll enter on this guy, and this will come up with an equation. And R squared of 0.997 means this is really fitting this data. If you want to see the data for yourself, I'm going to check this out in the window. Oh, let me turn on stat plot. Give me 1 second. And let me come up with the equation here. Vars, statistics, EQ, regression EQ. Let's see once again how these points fit in this data. There are the points. There's our curve that fits the data. Looks pretty good to 0.997 standards. How about? So what was our equation? Let's go back. Y equals A. Let's do 2 decimal places for each. So, or S equals 3.95 plus 27.48 times the natural log of T. So our equation is going to look like this with quite some accuracy there. That is a model that functions our data. It says estimate how many pairs of shoes are sold after 6 weeks. Now our table shows weeks 5 and 7, and you can see an increase in this. Therefore, it's going to be somewhere between 48 and 58, and it's an interpolated value, which means I can trust it within the domain pretty well. So let's go back to here. I did make the equation in here, which is nice. So I can either go to the graph and hit value, go to second trace and go to value and type in 6. This will give me the value for y right there, 53.18. Of course, how many pairs of shoes? I'll say 53. What I could also do is go to my table. If I go to ask, I can ask in the table and I can set it equal to 6 right here and find that same number, 53. So in this equation, we'll say S of 6 is around 53 pairs of shoes. 53 pairs of shoes. That's after 6 weeks. All right, and that's it. All right, guys, that'll do it for this one. This is Mr. Rums, and thank you so much for watching this Chapter 5 review. I hope that I slowed things down enough to take care of them. I'll also do the Chapter 5 test and cumulative assessment, for which I go faster on. I don't teach the stuff as slowly, so I could probably cut this in half the time if we had that kind of duration of problem. So get ready for that one. It's going to be linked. You can either find the playlist here or, whatever. You can find it linked somewhere else. Have it recommended to you. I'm not sure. But, guys, thank you so much. Take care. I will see you in that next one.